Welcome to another episode of Dave Does Math from Home. We have a good one for you today. Today we are talking about section 15.1. We're skipping chapter 14. I don't remember what it's about, but I remember that it is unimportant. Skipping 14, we're going straight to 15. This is 15.1. This is when we're going to get into functions and level curves. So we're going to spend chapter 15 just dealing with functions, and I think we're going to get into derivatives of these functions by the end of 15. We're going to start with functions in general. These functions are substantially different than the functions we've worked with before. I've mentioned this in a couple other videos where we're not dealing with two-dimensional functions anymore, where we have one independent variable x horizontally and then one dependent variable y vertically, and it creates sort of a curve on the plane. The variables we're going to, or the functions we're going to deal with in this section are all going to be surfaces. So we're going to take the entire xy plane. The entire plane is going to be an independent variable. So x is independent. We can pick any position we want along the x-axis, and y is independent. We can pick any position we want along the y-axis. That means that the variables that we are going to input into our functions, we're going to input ordered pairs. And the output will be a z value that is some distance above or below the plane. That's the third axis. Z is coming straight out of this. And again, when I do things on this sort of vertical surface whiteboard, we'll say that Z is coming out of the surface at us. So positive Z is in this direction, negative Z is behind the whiteboard backwards. If you're doing this on a piece of paper on a desk or something, then I think it's usually best to leave X going to the right, Y would be going sort of like up the paper away from you, and then Z would be coming out of the paper straight up if your paper is horizontal. That's usually how I sort of orient. One of those words. That's how I configure this set of three-dimensional axes in my brain when I'm thinking about this or doing problems like this. And so we end up with functions that take x and y as both independent variables, which means that you can pick any point on the entire plane that you want and plug that point into the function to learn how high above this plane you are on your surface. This is dependent. And we've already seen a couple really quick examples of this. We in section 13.2, I think it was, one of the, I think it was, yeah, the second vector chapter we did. We were looking at equations of spheres and equations of, I think we did a couple planes. I think we did very basic planes. X equals something. It's a plane. You fix an x value and you get a plane coming out like this. If you fix y at something, you get a plane coming out this way. If you fix z something, you'll get a plane that is parallel to the xy plane. So there's a couple things we need to talk about with respect to these functions. One is just sort of like a basic rundown of some common examples of functions we're going to work with. So like when we're doing functions in two dimensions, we kind of have this library of functions to choose from. We know that sine waves do the wiggle thing, and we know that parabolas are kind of like hooked upwards like this. We know that logarithms do a big swoop. Like we have this wealth of information that we're just familiar with and we can sort of understand the shapes of pretty intuitively. So we're going to try to build up something like that in 3 dimensions. 3 dimensions is going to give us a lot more weirdness there's a lot more, it's much, let's say, it's much more difficult to categorize functions in 3 dimensions into nice, easy, this was a logarithm, this is exponential, this is polynomial, this is trigonometric. Like those categorizations are very like straightforward in 2-dimensional functions. In 3-dimensional functions, things are going to get weird. Like something might be logarithmic along one axis and trigonometric along another. It's weird stuff's going to happen. But there are a couple still sort of like standard issue, like regular-ish functions that we're going to play with. So let's start with something like z equals 10, no, let's do 12. Z equals 12 minus 3x minus 2y. This, I think, is a good example of demonstrating that z is a dependent variable. You get to choose what x and y are. That's us inputting the ordered pair as an independent variable. We get to choose both, and then based on what we get for here, that'll tell us what z is. Hopefully we can sort of recognize this format as being linear. In 2 dimensions, linear functions make lines. That's what they're named for, in fact. But the characteristic of them isn't that they're lines. The characteristic, like the defining characteristic of linear functions is there's like no weird stuff, and they're first-degree polynomials, essentially. And the good news is that this is, for us, a first-degree polynomial. There's no weird stuff involved. There's no trig, logs, variable exponents, negative exponents. All our exponents are whole numbers, and in fact, all of them are either 1 or 0. That's what makes it linear. In 3 dimensions, the linear functions create a plane. And in this case, I'm going to try to do some kind of 3-dimensional stuff. I like having z go upwards. We'll put y over here and x over here. So these are actually kind of not terrible to draw. If you plug in the point 0, 0, you'll see that our z-intercept here is 12. So you're up here at, this point is 0, 0, 12. That is your z-intercept. If you want an x-intercept, that means that z and y are both going to be 0. So you would get 0 equals 12 minus 3x plus or minus 0. So we can see from that x would need to be 4. There's your x-intercept. That's 4, 0, 0. And if we wanted a y-intercept, then we would set x and z equal to 0, and we would get 0 equals 12 minus 0 minus 2y. And hopefully we can see from that y should be 12. Or, yeah, 6, sorry. 1, 2, 3, 4, 5, 6. So this would be the point 0, 6, 0. And then we have a plane. It sort of goes diagonal this way. So it does sort of make this, if you're only looking at this in the first octant, it creates this sort of lopsided triangular pyramid, which has right angles here, and so like the side face would be a right triangle, and this face would be a right triangle, and the bottom is a right triangle, and then there's the plane itself is what connects those 3 right triangles together. But you have this plane that sort of starts at 12 and swoops downwards. As x increases, it swoops downwards with a slope of 3, and as y increases, it slopes downward with a slightly more gentle slope of 2. And if you go backwards on either of those axes, the plane will increase. I feel it's hard to sort of gesture three-dimensional shapes at a whiteboard in front of a camera. Hopefully it's making some sense. If not, I'm not sure how much more I could do, but I could try. If you have suggestions for me, let me know. So this is a plane. Last thing I should note about the plane is that I mentioned that this is a polynomial. One of the kinds of questions that you'll get a lot of in this section's homework assignment is about domain. There's lots of questions about what the domains of different kinds of functions are. And as usual, the really, really nice thing about polynomials is that because there's no weird stuff, it means there's no domain restrictions. So if you get any kind of polynomial at all, there's no domain restrictions, you're good. Especially if you get something planar. This is it's like a line, it's like a straight line. It's just plain. It's a straight line with an extra dimension involved. But it has many of the characteristics of a straight line. It's got slopes, it's got intercepts. It's pretty nice. Another example I want to go through is spheres. We've already talked a little bit about spheres, but we talked about them. When we talked about spheres, they looked like x squared plus y squared plus z squared equals r squared. This is how we've worked with spheres so far, and it is very straightforward. I like that it's straightforward. The problem is it's not technically a function because it doesn't pass the vertical line test. If we try to solve this for z, we'll get the square root of r squared minus x squared minus y squared. But we'll need to do some sort of plus and minus business. So, as usual, the rule for functions is you can't get two different outputs from one input. So this is technically not a function. We're going to ignore that a lot of the time. We're going to sort of deal with this and play with this and treat it like it's a function because it has many of the other characteristics of a function, and we're often very interested to see how things behave on spheres or through surfaces of spheres. So we're gonna come back to this idea a lot. So don't completely disregard it. Just sort of when we need it to have all of the characteristics of a function, you have to sort of treat it as if it's two halves. This is the top half of the sphere, and then this is the bottom half of the sphere. So you can treat things that way. The other interesting thing, I guess there's a couple more things I need to say about spheres before we move on from them. If you put numbers here, so if you have something like z equals the square root of some sort of r squared minus 2x squared minus 4y squared. If you put coefficients in front of these guys, you end up with an ellipsoid, which is, so a sphere is what happens to circles when you make them three-dimensional. An ellipsoid is what happens to ellipses when you try to make those three-dimensional. You end up with kind of like a football shape. Depending on what these coefficients are, they might stretch or squish the thing in certain directions. If you put something here, or I guess I don't want to put anything there. Yeah, no, never mind. Putting numbers here will stretch and squish this in various dimensions, so that makes ellipsoids. They sort of behave almost always just like regular spheres do. They're just a little squished or stretched in some areas. both ellipsoids and spheres have domain restrictions that we need to be careful of. If we're doing some kind of like, if we want a radius 5 sphere, then we need to put a 25 here. This gives us a domain restriction that's sort of atypical. It's not really what we're used to. The domain restriction this gives us is, if you factor out this negative, we have to have x squared plus y squared be less than or equal to 25. If this sum is bigger than 25, then we'll end up taking the square root of a negative number and it's not going to work out. So spheres give us this domain restriction, and this domain restriction I think makes a lot of sense when you think about the geometry of it. If you're talking about a sphere of radius 5, you can't plug in points that are farther than 5 units away from the origin. You can't take a point that's distance 8 from the origin and see what height it has on a sphere of radius 5, because it's not inside that sphere. The only points you can plug into this function to get a sphere of radius 5 have to be closer to the origin than 5 on the plane. If their distance from the origin is exactly 5, then you're on the plane. If your distance from the origin is less than 5 on the plane, that means you have a height or a depth above or below that plane. And your three-dimensional distance from the plane is still going to be 5. For things like this, you can still sort of factor out this negative and then say that whatever this is has to be less than the radius. The radius here is 13, then this x squared plus y squared business with its coefficients still has to be less than 13. That's sort of how you extract domain restrictions from spheres and ellipsoids. Before I move on from spheres and ellipsoids, the other thing I really want to say about them is this is something that you'll see a lot in a lot of different functions. I mentioned that functions get really sort of weird sometimes and wild and out there, and they do, it's true. A lot of times the functions we're going to want to play with, the surfaces we're going to want to play with, are basically like, what happens if we take this shape and sort of like spin it around the z-axis so we get like something that's round, or something that has rotational symmetry, like a sphere. And in those sort of very roundish looking surfaces or roundish looking functions, you'll see this expression happen a lot. X squared plus y squared is something you're going to see in a lot of these things. That's how you get things that are round. I see that I'm already at 18 minutes, so I'm going to cut this video here, and then I'll make a new one where I can start to talk about some round things, like how you get like a mountain shape in three-dimensional functions.